I hope you see my screen and you hear me talking.
Exactly.
Well, yes, thanks a lot. So yes, I'm Dmitry SOLNYSHKOV. Good morning, ladies and gentlemen, and it's a pleasure for me to give this talk here. Well, I will speak about indeed analog chromodynamics, and it's a collaborative work between Lecce and Clermont-Ferrand. So indeed, in my talk, in fact, there will be an introduction once again about gauge fields. So we will see which introduction you prefer, mine or the one given by Vanya. And then I will show you that actually we are all doing somehow some kind of theoretical and chromodynamics and experimental chromodynamics when we are working with spin dynamics like Rashba, Risselhaus, or some other effects. Well, let's start with the simple case, electromagnetic field and gauge invariance. The idea behind the gauge fields is that we start with something which is known. The gauge freedom means that we have the scalar potential of the electric field, which is defined up to a constant. Indeed, the electric field is a gradient of the scalar potential. So if you add the constant, then the electric field doesn't change. The same applies to the magnetic field. It's a curl of the vector potential. So if you add the gradient of an arbitrary function, the curl of the gradient is 0 and the magnetic field doesn't change. These equations are valid for static fields. And this has given an idea which appeared in the middle of the 20th century to find a new way to write the equations for the fields. So in the case of the electromagnetic field, the equations were already known. But this way allows to find the equations even for the fields for which we don't yet have the experiments, for the new fields that we just don't know. The way is the following. First, you say that, okay, there is some gauge invariance for the wave function as well, for the wave function which describes the charge distribution. We know that we can choose arbitrarily the phase of this wave function. And then we say, let's suppose that there is a local gauge freedom. So this phase can be chosen arbitrarily from point to point. And then we require the gauge invariance of the Lagrangian, which contains the kinetic energy term and the mass term. Here it's written in the relativistic form. And it turns out that, of course, if you change this phase of the wave function from point to point, these derivatives, they will change as well. And to compensate for this change, you need to add some extra terms in the Lagrangian so that it remains gauge invariant. And these extra terms actually make appear the vector potential in the covariant derivative in the kinetic energy, and also an extra term appears, which is the 4 tensor of the electromagnetic field. And for the electromagnetic field, it contains the derivatives of the vector potential. It contains both the electric field and the magnetic field. And from this action, by varying it and using the corresponding equations, this action principle, you can derive either the equations for the field or the equations for the charge, depending on whether you vary psi or f. And then you can, for example, use the same approach to find some new equations for some new fields that you just don't know. In this case, for example, from this Lagrangian, you can obtain the Hamiltonian that you all know very well of the quantum particle in an electromagnetic field, where you have the vector potential and the electric potential together. And we will use this equation. It will appear many times. And Young and Mills in 1954 have applied this approach to a vectorial charge. So they have supposed that, at that time it was the isospin, a vector which describes if a particle is a proton or a neutron. It's a kind of effective spinor. And so we have a vectorial charge. In this case, the Lagrangian, in presence of the corresponding gauge freedom, has the same shape as before. You have the covariant derivative, and this covariant derivative contains again the vector potential. And you have also the field tensor in the Lagrangian. The difference is that the charge is a vector. So here we have a scalar product, and here as well we have a scalar product. But moreover, everything else are vectors and matrices. For example, each component of the field tensor is now a vector. And to understand this a little bit better, we can consider this component of the vector potential. So there are actually two spaces, completely independent in the general case. There is a real space, or rather space-time, where we have the t, x, y, z components, and then there is a spin space. And to underline the fact that the spin space is different from the real space, we will number these components 1, 2, and 3. So the Pauli matrices in this talk, we will call them sigma 1, sigma 2, and sigma 3. Very well. And in this field tensor, which is now composed of vectors, so each component of the tensor is a vector with 3 components in the spin space, there is an extra non-abelian term which appears because all operators acting on the vector, which is the spin, are matrices, and the matrices do not commute. And yes, it is very important that we don't have only the derivatives of the vector potential, but just the product of the components of the vector potential. So the field can be non-zero even if the potential is constant. It's not at all the case for the electromagnetic field. We really need gradients. Here we can have a constant vector potential. And from this Lagrangian, we can derive both the equation for the fields, but this I will leave to the end of the talk. I will focus on the charge dynamics. And we can write the simplest case, the charge dynamics equations in the classical approximation. So it's not a quantum particle, it's a classical particle. And in fact, the equations are quite simple because they represent the second Newton's law. The mass times the acceleration is equal to the force. And the force which appears here is really the Lorentz force. Only it acts on a spinor charge, on a vectorial charge. This spin current which appears here is a product of the spin and the velocity of the spin. And the force here is just the magnetic field, or it can be the electric field if it's this time-like component. But since the charge is now a vector, it can change with time. When it was a scalar, the electron's charge did not change, it was a constant. And a vector can change even if it keeps its length constant. It can still rotate. So we need another equation, which is the precession equation. How does this spin evolve with time? And actually, it evolves according to this precession equation, which has the natural shape. There is some vector potential, which makes rotate the spin. Finally, I would like to stress once again why it is called chromodynamics. Because this spin can be very general and it can apply to any degree of freedom. And in the case of quarks, for example, well, to stress the fact that it's not linked with the rotation and to invent a new word for a new degree of freedom, they have used the word color. So in fact, well, this degree of freedom to which it applies in strong interactions is called color. So it's chromodynamics. But in our case, it will be some other type of spin. So indeed, some emergent non-abelian gauge fields were discovered for different types of spinors. For example, for the electron spin or for the photon pseudospin. The mapping between the Young-Mills field and the Rashba field was done in 2006. Then we have ourselves suggested a similar mapping for exciton polarities or for photons in microcavities in 2014. It was independently discovered for electromagnetic field in a more general case in 2019, and even electrostatic-like non-abelian experiment with light has been published in Science in 2019. So now it has become really a strong subject of research. And let us go deeply into details of this subject. So how can we see the Rashba spin-orbit coupling as an example of a Young-Mills field? Let us compare the Rashba Hamiltonian with the Young-Mills Hamiltonian. Well, first of all, we write the Rashba Hamiltonian, and it is, okay, it's not completely Rashba, it's a monopolar field because it's the simplest way to write it. So we have the kinetic energy, and then we have the spin-orbit coupling, a scalar product between the Pauli matrices, the spin operator, and the momentum. And then we can rewrite this Hamiltonian as by adding and subtracting a constant term. We can rewrite it as a square of a sum. And in this parenthesis, we have the momentum and also some term with the Pauli matrix. And it looks indeed very much like the way you introduce the electromagnetic field. The vector potential appears here in the parenthesis with the momentum. If we look at the Young-Mills Hamiltonian, which you can obtain from the Lagrangian that I have shown you on the previous slides, in the non-relativistic case, so it's simpler, but it is for a quantum particle here, then we see that it should be written the following way. There is a momentum in the parenthesis, and then you can have some arbitrary set of Pauli matrices linked with some arbitrary components of the real space. So it means that you can have actually px and some other Pauli matrix like sigma x, sigma y, and even sigma z. It depends on what components of the vector potential are non-zero here. Don't forget that we need to call in this talk the Pauli matrices sigma 1, 2, 3. So in our case, we have the monopolar field. It means that we have sigma 1 px and sigma 2 py. And that's why the components of the vector potential ax1 and ay2 are non-zero and they are constant. But since our gauge field is non-abelian, the field tensor is non-zero even if the vector potential is constant. The derivatives are zero, but this vector product is non-zero. So it gives us two non-zero components of the field tensor, fyx3 and fxy3. And well, since they are non-zero, there will be some force. And we can calculate the effect of this force, and we can predict an expected consequence. There will be a Lorentz magnetic-like force acting on a spin current. There will be some acceleration. So if you have a spin current propagating in the x direction, jx, composed of spin-up particles, then they will be accelerated along y direction, so in the perpendicular direction. That's why we say that it's a magnetic-like force, because it accelerates particles in the transverse direction, but it acts on a spin current. You really have to have a spin. Okay, and it turns out that using their approach, Young and Mills, so using the gauge field principle, have discovered the Rashba effect and the Dresselhaus effect before Rashba and Dresselhaus, because their Hamiltonian describes both Dresselhaus coupling and Rashba coupling, and it was obtained in 1954, before Dresselhaus, which was 1955. So indeed it works. You can discover new fields. Now, what we have done ourselves in 2014 is to consider a microcavity with TTM and a birefringence or XY splitting. TTM gives us a dipolar texture of the effective field in reciprocal space, but if you add the birefringence, you obtain some splitting at k equals 0 and some crossing of the branches at some non-zero wave vector, because the two branches have different masses, and so the one which grows faster has to cross the other branch. And in the reciprocal space, it splits the point-like dipole texture into two well-defined monopoles, one of them divergent and the other convergent. And around these regions, you have really a Rashba-like effective field, so which you can represent using the minimal coupling Hamiltonian, the Hamiltonian that I have shown you before. And the consequence that we have, one of the consequences that we have discovered in this work in 2014 is that the scattering on a defect of polarity and flow is strongly modified. Without the gauge field, you have normal interference and some diffraction behind the defect. And with the gauge field, there is really a change of the pattern with some kind of focusing. The beam is concentrated behind the defect. And at that time, we have described it using the dispersion of particles, but not using the language of Young-Mills forces acting on the fields. And this is what we will do in this talk. So this work has an experimental part, which is done on the perovskite microcavity in Lecce. And this perovskite is a 2D material with interesting properties. For us, the most important one will be a reasonable birefringence. But it also has a strong coupling with light with a Rabi splitting of 200 MeV, so quite strong Rabi splitting. As to the birefringence, why it is important to have a strong birefringence? Because it gives us a strong splitting at k equal to 0, and then this point where you can observe the gauge field moves sufficiently far away from 0, because the crossing occurs at the point which is given by the square root of birefringence divided by TTM. And you need to have both of them significant to obtain some measurable effects. So it's very good to have this type of material. We see a crossing in one direction, no crossing in the perpendicular direction. But if we focus on this point and we make a cut at this point in the perpendicular direction, we really see the typical dispersion corresponding to the Rashba Hamiltonian, linear crossing at k equal to 0, ky equal to 0, kx equal to this crossing point, and then some parabola. And indeed, we see that, in fact, these two parabola, which we are used to in the Rashba Hamiltonian, they look very much like the vector potential effect, because if we look at this Hamiltonian of the electromagnetic field, the effect of the vector potential is really to shift the minimum of the parabola to the left or to the right. And it's also important to see that we have both linear and parabolic contributions, and none of them can be neglected in this case. The spin texture in the reciprocal space is as expected, and it shows a divergent and convergent monopoles at points at this energy level. Now let us discuss the experiment number 1. It is well, the idea is simple. We need to create some spin current to observe some transverse acceleration. So let us inject polaritons propagating at some non-zero wave vector with some well-defined spin. If their spin is oriented upwards, so these are spin-up polaritons, S3 component is positive, then there should be some negative acceleration along Y, and they should be deviated downwards. If they are spin down, they should be accelerated upwards. But we shouldn't forget that there is a second equation of the classical chromodynamics, or just spin precession equation. If we have some spin and some constant vector potential, or we can call it effective field, then the spin will precess about this effective field. And so after some time, instead of remaining spin up, it can become spin down. And then particles will be accelerated in the opposite direction. And this is what is observed in experiments. So when we inject spin-up particles, they are accelerated downwards. But then the spin is flipped and then they start to be accelerated upwards. If we inject polaritons with no spin, which means that the spin is in the plane, so no S3 projection of the spin, there is no transverse acceleration. They remain at y equal to 0. Finally, if we inject spin-down polaritons, they are first accelerated upwards and then downwards. And this is well reproduced by quantum simulations. Of course, we can say that we use the Spinor-Schrödinger equation for polaritons with the TTM and the Birefringence, but we can also say that we are doing quantum chromodynamic simulation for a quantum particle in a Young-Mills non-abelian field, gauge field. The equations are exactly the same. And well, of course, I was showing you the trajectories and saying that the spin is flipped at this point, but it doesn't appear on this slide. So we need to plot the circular polarization degree, or S3 projection of the spin, or color. And these colored points come from the experiment. So we see that if we inject spin-up particles, these are red points, and then they are accelerated downwards, and then the color changes, they become blue, and they become accelerated upwards. And the opposite happens if we inject spin-down particles. And this is well reproduced by equations of classical chromodynamics, or by the equations of quantum chromodynamics, which take into account the fact that the wave packets have finite size and they can split. The transverse profiles are shown here, and I have even better transverse profiles as a waterfall plots. We can see that, okay, the center of mass does not necessarily correspond to the maximum of the wave packet, and the wave packet can have a complicated shape because of the disorder and because of the wave packet splitting, but it is undeniable that there is a global shift of intensity to the left in the case of spin-up particles and to the right in the case of spin-down particles initially injected. I would like to stress that the center of mass is very useful for such type of experiments because the uncertainty on the center of mass position actually decreases with the wave packet size. Whereas if you would be working with the maximum of the wave packet, in this case, if you have a broader wave packet, of course, the precision decreases. The precision decreases and the uncertainty increases with the wave packet size. Then, well,
3 minutes.
To show you, thanks a lot. To show you where this polarization for the colored points was coming from, here is the polarization resolved data in log scale. We see that initially we have spin-up polaritons, but because of the spin conversion, there is no more spin-up particles in the second half of the propagation, whereas there are still some spin-down particles, and when they become spin-down, they start to become accelerated upwards. So these points were really coming, of course, from the experimental measurements. Now the experiment number 2, it is more complicated. So we have some polariton flow, which is unpolarized, which is polarized linearly. So it's in the plane and we don't have some spin projection along the vertical axis. It is scattered on a defect. And in the first part of the scattering, actually the first equation is not playing any role because the polaritons are forced to propagate along the defect. But the second equation still plays some role. There is a precession because the propagation direction is such that the spin is no more aligned with the vector potential or the effective field. So it starts to precess, and it precesses in opposite directions. So you get some spin down component when going downwards and some spin up component when going upwards. And then when you are at the level of the defect, you finally do have some spin current, and this spin current is opposite at the two sides of the defect. And finally, the Young-Mill forces start to act and they accelerate your polaritons towards the center of the system. And that's why they converge behind the defect. And this is what is seen in experiment. You see the maximum of the intensity here going downwards from the upper part of the defect and upwards from the lower part of the defect. And in the quantum simulations, quantum chromodynamic simulations, you see the same thing. There is some convergence behind the defect. And this is well reproduced by the classical chromodynamic simulations, showing the spin down and spin up that converge behind the defect. And finally, some polarization maps to end this talk. So in the experiment and in theory, the best way to plot this is to use the S2 spin component because of the rotation of the spin. With the best contrast is achieved in S2, and you see really that there is a flow of S2 towards the center. And the simulations show that indeed there are opposite spin currents above and below the defect, and that's why you have some acceleration, opposite acceleration towards the center of the system. And so this has confirmed our predictions of 2014. And the conclusions are that I hope I have shown you that non-abelian gauge fields are interesting, not only to high energy physics, that we are actually all doing some non-abelian gauge and Young-Mill simulations when we study some Rashba spin-orbit coupling. And maybe our understanding of Rashba physics can even help with quarks because we do understand them quite well. And the next goal is to obtain some analog gluons, because actually another peculiarity due to the non-abelian nature of the field is that even if in the absence of the charges, the divergence of the non-abelian gauge field can be non-zero. It means that the field acts as a source for itself. For the electric field, when you don't have any charges, you have zero divergence. For the Young-Mills field, it's not the case. So the next goal will be to reproduce these nonlinear fields in some polariton system. Thank you very much for your attention.
Thank you very much, Dima. Thank you very much for this very nice talk and these fine analogies with high energy physics. So the paper is open for discussion, and we already have a question from Alexei Kavokin. The next will be Ivan Shilych. Alexei, please.
Thank you, Dima. If we consider this problem from the point of view of classical optics, so we have the scatter that generates a cylindrical wave, and we have a plane wave that propagates behind the scatter, and then there is some interference. Of course, well, polarization should be taken into account. So using this simple language, would I be able to describe all this phenomenology, knowing nothing about gauge fields and etc.?
Yes, and that's precisely what I mean when I'm saying that we understand Rashba physics. Because, okay, if you use the language of classical optics, taking polarization and spin-orbit coupling into account, it means that you know that the dispersion has some particular shape. And this is how we have explained this effect in 2014. The fact that actually you have some crossing at this point of the two dispersions, and this deviation here is due to the transverse group velocity. So yes, but the point is that it is this way that we can help to solve the problems, the complicated problems of chromodynamics, by this understanding that you can use the language of dispersion to describe such things, but you can also use the language of, actually magnetic-like force acting on a spin current. So this deviation, you can say that either it's transverse group velocity or that it's a force acting on a spin current. Both are true.
Thank you. So next question, Ivan.
Yes, actually, I have two comments. So first one regarding your first experiment about the dynamics of the center of the wave packet. So there is actually the term for this kind of dynamics. It's called Zitterbewegung. And what we're reporting here, this is Zitterbewegung. I was thinking that Alexei Kavokin will make this remark. Actually, yes, in their work with you, they demonstrated, So they demonstrated that the similar type of dynamics will happen only if you have just TATM. You don't need this additional in-plane splitting.
Yes, I agree. Well, I agree with the fact that in general, oscillating dynamics is called Zitterbewegung. Then we should make a remark. And in this sense, of course, you don't even need gauge fields. Whenever you see some oscillations, you can say that it is Zitterbewegung. Then another important point is that actually the original Zitterbewegung was obtained by Dirac in the Dirac equation. And moreover, it's a Dirac equation with the mass term. And in this Dirac equation with the mass term, you see my screen now with the PDF file.
Yes.
In this Dirac equation with the mass term, there is no gauge field. It's just, so it's a completely different equation. Just it can exhibit similar effects because there is also a spin and there is a spin precession. But it is not, well, not the same equation. So it's not the same Zitterbewegung, but it is some oscillatory motion. Another point is that actually our, in the case of, well, the behavior is not limited to Zitterbewegung in the case of gauge fields. They do have some solutions which exhibit, for example, Landau-like behavior, cyclotron orbits, 6 cyclotron orbits. And I think that for this Dirac equation, it's not the case. And yet final thing is that even this mass term can be represented as a gauge field, a kind of Higgs mechanism, if you can see this term as a result of a constant gauge field. But you have to rewrite your Hamiltonian saying that you have massless particles, some extra gauge field non-zero acting on them, which creates their mass. And that's why you can say that, okay, Zitterbewegung in different systems is somehow similar, but the Hamiltonians are not exactly the same.
No, I think you completely missed my point. So my point was that even in the microcavity without this Rashba type splitting, just T10, yes, you will have similar effect.
Yes, I agree that oscillating motion, which is in German called Zitterbewegung, can be seen with many different Hamiltonians.
Yes, yes, but like you present experimental results as well, so it's not a demonstration of your Rashba thing. It will be the same for the T10, only T10.
Well, I don't need to, no, it will not be the same. There will be some oscillating motion. I don't need to demonstrate that I have...
the same. Qualitatively the same.
Well, for you, of course, maybe all oscillations are qualitatively the same, but it's not the case in real life. I mean, there are different oscillations. We don't need to demonstrate that we have the Rashba Hamiltonian. It is shown experimentally on this slide.
Gentlemen, although for me it is very pleasant to hear this discussion as back in the old days in Clermont, I think that we have to move on. We have one more question from Jacek Żytka. I'm sorry for not pronouncing the surname properly.
Dmitry, thank you very much for the insight into Rashba-Dresselhaus spin orbit interaction. I would like to ask you a question about the role of polaritons in your calculation. It means that is it that just the effect of birefringence of your system? That means that what was actually Barbara was showing at the first lecture on the conference, that this is the propagation of light in the modes, in optical modes, and then the polaritons or the excitation, light matter excitation, is not as important for your calculation, although very beautiful and
yes, you are completely right, and that's why this paper of 2014 was entitled "Photonic Cavities." You don't need really the excitonic part to have this effect, but it brings some advantages. And one of the advantages is the fact that you, well, if you have some exciton, it means that depending on the detuning, the dispersion changes. So if you miss your parameters at some point, when you move higher in energy, you will have a better crossing. So the crossing region will be different for different branches. In this sense, well, you have some more freedom. But in the sense that, okay, right here, the excitonic part is not used at all. It's rather when, for example, you would like to apply some magnetic field in general and see some Berry curvature at this point, some anti-crossing. In this case, it might be important, not for this particular work on chromodynamics. And that's why here it's written with photons in a perovskite microcavity. The fact that we do have strong coupling does not play a strong role yet for these chromodynamic simulations, experiments.
Thank you.
Okay. Are there any other questions or comments? I do not see any. So I think it's time to conclude this session. Thank you, Dmitry, once again, and thanks to all the speakers of this session. It was really enjoyable, and thank you very much. And unless there are some